Welcome to Session 12, Coordinate Geometry, Slope, Distance, and Intersections. This lesson develops mathematical reasoning that stays reliable when a problem looks unfamiliar. You will learn to interpret slope as change, to find intersections algebraically, and to derive distance from coordinate differences. These are connected habits, not isolated tricks. Keep a pencil ready. We will build a mental model, use a repeatable method, solve a demanding example, diagnose an error, and finish with an independent checkpoint. Start with this principle. Coordinate formulas encode geometric relationships. Use this visual structure. S-slope equals rise/run. Distance equals sqrt dx squared plus di squared. Rate every symbol and label before calculating. The first goal is to interpret slope as change. Connect it to the second goal. Find intersections algebraically. Correct calculation begins with correct interpretation. When the surface details change, search for the same relationship underneath. Transfer means choosing the structure from evidence rather than waiting for a familiar-looking example. Step 1. Label both points in the same order. State the target and preserve its units or conditions. Step 2. Compute horizontal and vertical changes. Use a separate line so signs, factors, and labels remain visible. Step 3. Choose slope, intersection, or distance. Keep the reasoning efficient, but never skip an operation that could hide an error. Step 4. Substitute coordinates to verify. Verification is part of the solution because it tests the answer from another direction. Signal 1 is parallel lines. Respond by remembering, match slopes. Name the response before calculating. Signal 2 is perpendicular lines. In that case, use negative reciprocal slopes. The form tells you which tool fits. Signal 3 is endpoint distance is a diameter. Remember, halve it for radius. This separates plausible work from valid reasoning. If you cannot name the signal, pause and classify. A deliberate choice of method is usually faster than repairing a rushed setup. Here is the challenge. A line passes through 2, 3 with slope 4. Which equation is correct? Restate what is requested before touching the choices. The first move is label both points in the same order. Apply it directly to the quantities and conditions in this problem. Now use the core reasoning. Point minus slope form is y minus y1 equals m minus x1. Keep each equality, comparison, or unit conversion visible. Pause for a midpoint audit. Check copied values, signs, units, restrictions, and whether the current result is the requested quantity or only an intermediate value. Continue by applying this control. Choose slope, intersection, or distance. The explanation supports one option without relying on its position. The mathematical conclusion is y minus 3 equals 4 minus 2. State it with any required units, interval notation, or restrictions. The final answer is y minus 3 equals 4 minus 2. Compare it with the exact target and reject any choice that represents a common intermediate step. Verify from another direction. Plot or substitute the result back into the defining relationships. The check should use evidence independent of the original calculation whenever possible. Try this checkpoint without copying the example. Why should an intersection be substituted into both line equations? Decide which mathematical fact controls the answer. Pause and write one line of reasoning before committing. A visible decision is easier to inspect, explain, and correct than an unsupported guess. F-focused hint. A system solution must satisfy both relationships. Use the hint to repair the setup, then finish the reasoning yourself. The accepted answer is, to confirm the point lies on both lines. Explain why it works, and name the earliest line that would reveal a likely error. The central message is to interpret slope as change. Combine that with the discipline to find intersections algebraically. Finish by remembering to derive distance from coordinate differences. A result becomes dependable only when the method and verification are both clear. Reflection. Were both coordinate differences taken in a consistent order? Name the exact point where an incorrect path would first become visible. Practice one fresh problem for 8 to 12 focused minutes. Keep the work readable, verify independently, and carry the routine into the next session. Before moving on, close the notes and explain the method aloud from memory. Then invent one small variation, predict how the answer should change, and verify that prediction with a complete calculation.